Broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, my name is John DeBella, and on behalf of Simulations Plus, I welcome you to today's webinar where we will focus on the exciting new features in MembranePlus 2 and show how new outputs from the program can better inform your GastroPlus PBPK models. Jim Mullen, Principal Scientist and MembranePlus Product Manager, will be presenting today. Joining Jim as a panelist is Viera Lukacova, Team Leader for Simulation Technologies. An opportunity to ask questions will follow Jim's presentation today. You may either send your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. If you're using a telephone to listen to the call, please be sure to enter the unique audio PIN displayed when you join the call. When you enter your audio PIN, this enables us to unmute your line so that you can be heard. This webinar is being recorded for playback at the online resource center on our website, www.simulations-plus.com. Also, upon request, the presentation slides can be made available and shared with colleagues. It is now my pleasure to turn the presentation over to Jim. Jim?
Thank you, John. Today we'll be talking about the new features in MembranePlus 2 and hopefully stimulate your kinetic understanding. So let's go to the next slide. What is MembranePlus? It's a collection of models for cell-based assays that allow you to make predictions of permeability, metabolism, active transport in your cell-based assays. We've got two new models in MembranePlus to talk about today. We have a new sandwich hepatocyte model to predict the disposition of drug in the cells, as well as the bile pocket, and look at bile transporters in the sandwich hepatocyte assay. We also have a new suspended hepatocyte assay so that allow you to look at your clearance mechanisms and any active uptake in those systems as well. And then, of course, from version 1, we still have all of our permeability assays, CACO, MDCK, and PAMPA. These all provide inputs so that you can better populate your GastroPlus simulations. So, looking at the biliary excretion and active uptake in the sandwich hepatocytes, the clearance mechanisms for your CYP enzymes, and then your permeability or the effect of lysosomal trapping of lipophilic cations. You can enter all these as inputs and perform IVIVE in GastroPlus 9.5. How will it help you? Well, unlock important information from your measured data. If you have kinetic data, concentration versus time across a wide range of dosing concentrations, you can obviously pull out Km and Vmax values for transporters or metabolism. You can look at permeability from your measured data. It also allows you to design better experiments with our parameter sensitivity analysis features. You can look at the effect of different variables in your assay, different volumes, pHs, protein binding, things of that nature, to see what type of results you're likely to see with your experiments and design better experiments. Also, these models can all provide better and accurate inputs for GastroPlus simulations as well. And who should be using this? Obviously, GastroPlus users like myself, and probably many of you are looking to define inputs for lysosomal trapping, and also active transport and metabolism, in particular intracellular Km and Vmax values that are necessary for simulating PK and GastroPlus using the ACAT and PBPK model functionality. DMPK researchers that focus on performing these experiments can use the software to generate results as far as Km and Vmax values, permeabilities, and et cetera from the experimental data itself. And then discovery scientists can also use the ADMET predictor module functionality to predict from structure the permeability and clearance values for given compounds. So what I'll be talking about today, first we'll give you a quick overview of the program, how it's set up and what the interface looks like, what inputs go into it. We'll go into the model specific details, the physical situation of the different models and what's taken into account, and look more closely at the details involving the models themselves. And then finally we'll get into some case studies. One, quick model validation to see that our new models are doing what they're supposed to be doing. And then, but more importantly, the last three examples are going to be looking at the link between GastroPlus and MembranePlus and really look at how you can use the results that you obtain from MembranePlus to populate your GastroPlus simulations. So MembranePlus is a software platform that allows you to perform data analysis. And by that, I mean, take your kinetic data and extract permeability outputs from it. So, transcellular permeability, paracellular permeability, look at intracellular concentrations, whether they be the membrane concentration, cytosol, lysosome, things of that nature, the fraction unbound in the cell. Look at in vitro Km and Vmax values for enzymes and transporters, do parameter sensitivity analysis, and look at the important variables, for instance, log P, shaking rate, pH, protein binding, et cetera, in your cell-based assays. We also have added new models so that you can do data analysis for sandwich and suspended hepatocyte models to extract intracellular Km and Vmax values that can be input into GastroPlus to predict clearance of your compounds for those hepatocytes. So we can also do predictions as well from structure of permeability at the intracellular concentrations in the cells. We can predict the Km and Vmax values for 5 CYP enzymes for hepatocytes from structure using our ADMET predictor module. There's also, from structure you can predict FU enterocyte, the amount of drug unbound in the cells themselves in the intestine. You can look at CL diff, or the passive diffusion in your hepatocyte assays, and then all these can go into IV-IVE and better integration with GastroPlus. So there's many different membrane systems that you can simulate now in version 2. In red are highlighted the new features in the software. There's various different assays that you could choose from. The new ones are suspended hepatocytes and sandwich hepatocytes, as I mentioned earlier, but we also still have the CACO, MDCK, and PAMPA. Various well plate configurations are available, and any user-defined cell monolayer configuration can be defined, so you're not limited to what's built into the software. And then the processes that can be simulated are the passive transcellular and paracellular portion of the diffusion, unstirred water layer diffusion, carrier-mediated influx or efflux, metabolism in cells, fraction unbound in cytosol, passive diffusional clearance, binding to albumin, accumulation in cell membranes and intracellular compartments, the lysosomal trapping, which we'll get into in more detail, and then accumulation in the bile pocket for sandwich culture hepatocytes. So if we look at the interface really quickly, the first tab is the compound tab, and that contains all the drug inputs for your compound. We provide, you can use the ADMET predictor module to predict these compound properties on the left-hand side of the interface here, but they're standard phys-chem properties. Many of you will have laboratory access to experimental values, and you can use those values as well and enter them into the interface directly. We have on the right the initial dosing concentrations. You can dose to the donor or receiver compartment on the apical or basolateral side for, say, CACO assays. And then we have the passive transport model parameters on the bottom right. If we look at the next tab, the experimental setup tab, you can choose the type of membrane assay. We just mentioned the 5 different types of membrane assays that you can simulate. You can, on the bottom left, you can specify the sampling setup, so how much volume you're using when you're sampling the concentration out of the apical or basolateral compartment. And that has effect on the, obviously the concentration when you sample some of the volume. Protein binding, compound loss can also be specified, so any plastic binding to the surface of the wells. On the right is the experimental setup, and that's where you're really going to enter in the membrane-specific parameters for your experiment: the shaking rate, the volumes of your compartments, the pHs of your compartments, the filter area, the pore size of the filter, et cetera, et cetera. On the next tab of the interface, the simulation tab, it allows you to select the simulation mode. We have single simulation, batch simulation, or parameter sensitivity analysis. You can select from all of those. You can run a simulation clicking the start button, and then it'll display the results at the end of the simulation for concentrations in some of the compartments, the fraction unbound in the cell, the permeability, both paracellular and transcellular, any efflux or influx, and any losses to the plastic or sampling that's defined. You can also add optional observed values like the A to B or B to A permeability, and these can be used as optimization values. So if you need to optimize the permeability parameters for your model, you can do that as well. The graph tab allows you to display the end result of your simulations for the apical and basolateral side. This is just a prediction from structure of propranolol versus some experimental data, and we plotted the apical concentration in red and the basolateral concentration in blue. And then you can display the end amounts in the different compartments as well. New to version 2, we have Excel output reporting, so you can save all the simulation data from single batch and PSA simulations into an XLSX file. So that just removes a step, makes it easier for you to plot things in Excel on your own if you don't want to use the internal plotting engine. So that streamlines data output for everybody. Okay, so that's the interface itself. So now we're going to get into the physical situation and the mechanisms involved in our model and go through in detail what those are and what's being done behind the scenes in MembranePlus. So first off, we'll look at the Keiko cell assay. Here we have an apical solution, an unstirred water layer above the apical membrane, the cell layer itself, which is on a filter support, and then the basolateral unstirred water layer, and then the basolateral compartment on the bottom of the screen there. If we dose the drug to the apical compartment, we'll first get diffusion through the unstirred water layer to the surface of the cells, at which point the drug can permeate through the cell membrane. If it's a lipophilic drug, it can enter the membrane and then exit into the cytosol. It could be transported through active transport into the cytosol, or if you have PGP efflux, it could be effluxed from the cytosol back out into the apical solution. When the drug gets into the cytosol, it can be trapped within the lysosome. Lysosomes are structures that have low pH, and for basic drugs that have higher solubility at pH 4 in the lysosome, you can get substantial drug being partitioning into the lysosomes and trapping within those cellular structures. Metabolism can be calculated within the cell. And once the drug diffuses through the cytosol, it can then enter the basolateral membrane and then exit into the, through the filter support into the basolateral fluid. It could be also effluxed with, efflux transporters or influx from the basolateral side as well. There's, of course, paracellular diffusion, and this depends on the radius of your molecule, and that determines at what rate it can diffuse through the pore radius of the tight junctions there. At which point there's filter permeability, so the filter support provides some resistance to transport. In almost all cases, it is not limiting, but we provide that just to be thorough. And then there's diffusion through the unstirred water layer on the basolateral side. So all these mechanisms are calculated in the model itself. To that, we can add protein binding on the apical or basolateral side. So if you're using any sort of BSA or HSA in your, any albumin in your apical or basolateral solution, you can use the Hill equation or just specify fraction unbound to add those physics to the model. New in version 2, we have protein binding intracellular as well. So if you are able to measure or you want to predict some sort of binding in the cytosol, you can do that. And this can also be used for non-specific binding as well. So you can specify a fraction unbound in the cytosol, and that's newly available in all of the models. Loss mechanisms, as I mentioned, lipophilic drugs tend to bind to plastic, so you can have those types of loss mechanisms and non-specific loss as well, and then evaporation as well from the apical compartment. So that's looking at the CACO model. The sandwich hepatocyte model is, pretty similar. All the same mechanisms are there, and I've highlighted those in the image. The thing you'll notice here is there's not a donor and receiver phase. There's just a donor phase. The cells are attached directly to the well plate, so that you don't really need to worry about paracellular diffusion or any of these mechanisms. So it's a little bit simpler in terms of that. What we have added, though, is now we have bile pockets that are sandwiched there in the apical membrane, between the apical membranes of adjacent cells. And then we can have passive transport from the cytosol into the bile pocket through just passive mechanisms. And then, of course, we can have efflux from the cytosol into the bile, so biliary excretion. And again, protein binding in the cytosol are added. Suspended hepatocytes, again, all the same features. There's a couple differences with the suspended hepatocyte model. There's no differentiation, cell differentiation in suspended hepatocytes, meaning you can't really tell what the basolateral or apical side is in this case. These cells are just floating around in solution. So the transporters are just, we just call everything a basolateral transporter, but you can add any sort of transporter you want in the model and calculate the rates as needed. Again, in addition, we'll have the diffusion layer, but now we're doing everything in spherical coordinates. No longer are we on a flat monolayer of cells, we're in a spherical geometry, or we're assuming the cells are spherical. So this is another change to the model itself that we're accounting for. We've added extra parameters to account for the hepatocyte and the bile canaliculi. So we need to know what the contact area is between the bile pocket and the apical membrane in the hepatocytes. So we've looked up literature, found that there's about 10% of the contact area is the bile canaliculi. And then we also pulled out the total volume of bile in relation to the tissue volume as well. We've also determined, what the lysosomal volume is in the hepatocytes from the literature based on cell fractionation studies, and we've added that as to the models as well. So we've got improved physiological settings for our model. We got the new intracellular protein unbound and cytosol. We have the new additional values for the sandwich hepatocyte, the volume percentage and the area percentage for the canalicular membrane. And then we also have a bile contraction efflux rate to media. So this takes into account, if you have any modulators of your tight junctions, you can have drug release from the bile pocket to the basolateral solution. And so we have a first order rate that you can define to calculate that drug release from the bile into the basolateral compartment. So now let's get into the details of each part of the model. So we've gone over the physical situation, but let's dive deeply into each of these components of the model. So first, let's look at the unstirred water layer. Unstirred water layer is calculated based on the Nielsen paper, where they looked at, or they developed an empirical equation that relates the unstirred water layer thickness to the diffusion coefficient over a fitted parameter K times the shaking speed to a power X, which is another fitted parameter. We took the average values from all these different sources and added those to our model. So when you change the shaking rate in our model, it'll automatically update the diffusion layer thickness from that shaking speed. So that diffusion layer thickness can range anywhere from maybe 50 microns all the way up to close to 1,000 microns, depending on the, or greater than 1,000 microns, depending on the shaking rate that you input. This doesn't apply for suspended hepatocytes because that's a completely different geometry and whatnot. For suspended hepatocytes, we're making the same assumption as GastroPlus, that since they're freely settling particles in solution, we're assuming that the boundary layer is similar to the cell size. So the next transport mechanism that we want to look at is the membrane entry and exit rate. So the membrane entry and exit rate model is a structure-based model trained to CACO data for 44 experiments. It's based on the drug's log P, the presence of ring structures that are non-benzene, and then also hydrogen bond acceptor and donor features of the molecule. And these are all count-based descriptors. And this model was fit based on absorption systems data that they provided to us. So that's built in and calculates the input rate of the drug into the membrane itself. We also have a second model, which is a log P dependent model called the Combini model, which is from old literature from the 70s. And it's based simply on the octanol water partition coefficient. And so this works well for a cogeneric series of molecules that have similar, hydrogen bonding characteristics. Maybe they have different log Ps, but you can fit the model parameters gamma and delta, C and M, and then model the input and input rate of the drug into the membrane using that model. But it works well for cogeneric series of molecules. Direct input, you can also just specify these values yourself or optimize these values as you see fit using data. On the bottom right there, you'll see a depiction of the speciation of the compound at the surface of the membrane. So, the drug is going to exist in multiple forms, either the neutral form, cationic, or anionic form. Based on the log D versus pH profile, we can calculate the input rate of that cationic or anionic drug based on the log D versus pH profile. And so we can do that for those cationic and anionic species. Obviously, the permeability rates for the cationic and anionic species are going to be much less than the neutral species based on the log D versus pH profile. We also have paracellular diffusion. This is going to be critical for compounds like mannitol, atenolol, that have very low lipophilicity and are small in size and can, really work their way through the paracellular route. So we have two different models, the same models that are in GastroPlus, the Adson model and the G-Min model. The Adson model assumes that the molecule is a spherical radius and then it moves through pores. As such, the G-Min model assumes that the molecule is a football shape with two radii, a major and minor radii. I say football shape because it's football season, but really it's an ellipsoid. There's physiological parameters that are built into this. The most important are the intestinal electrical potential gradient that modulates positive versus negatively charged permeability rates through the tight junction, and then the pore radius. These parameters were fit using mannitol and atenolol, and where available, they were taken from literature. The filter support is modeled in the same way, but in this case, the radius of the pore sizes are usually much, much larger than the molecular radius itself. So the membrane provides very little resistance to transport, but you can add that functionality into the model as well. There's default values for the pore size, pore density, and filter membrane depth taken from literature specs for these Transwell plates. The next mechanism, let's look at active transport and metabolism in the cells. So we model everything as a carrier-mediated transport metabolism process using Michaelis Menten kinetics, and this is important. We don't assume any linear clearances. A lot of what you'll find in the literature, people will use uptake clearances or, metabolic clearances. In reality, many of these processes are saturable, and so we like to model everything as a Km and Vmax for metabolism and efflux or influx. Critical here is we use the intracellular concentration to define the metabolism and efflux from these cell-based assays, and these are the same parameters that are going to be used within GastroPlus to define either say the efflux in the intestine, PGP efflux, or the metabolism in the liver hepatocytes themselves. So these are, knowing the intracellular Km and Vmax are critical inputs for doing IV/IVE, and these are the types of models that we build in our in vitro system. For biliary efflux, again, it's using the intracellular concentration as well, so to predict the efflux into the bile. Lysosomal trapping. So lysosomal trapping for lipophilic cations. So at higher pHs, the basic compounds are going to be, let's say, more neutral. Neutral compounds are very permeable to membranes. So, at pHs 7, 7.2, 7.4 in the plasma or cytosol, the basic compounds can readily permeate, get into the cell and permeate the lysosome, get into the lysosome. In the lysosome, the pH is about 4, and if the PK is 6, 7, 8, you're going to see much higher solubility in the lysosome than the cytosol or plasma compartments. What happens then is the equilibrium between the neutral form and the cationic form is skewed towards that cationic form, and you're going to build up a large concentration of drug in the lysosomes. And so there's a storage mechanism, which is basically a sink for drug as it's going through your intestine, permeating through into your bloodstream, into the portal vein. So what this does is causes a lengthening of the Tmax, or as you can see here on the right-hand side in the table, for these lipophilic basic compounds, the PK is, you see very long Tmaxs for these compounds. And the theory is, and I think it's been proven and it's been published in the literature, that these drugs are storing in the lysosome and slowly being absorbed into the portal vein, thus stunting the Tmax or lengthening the time until the Tmax is reached. So that's one thing that we can calculate within the simulation. And this is an input into GastroPlus, and we've seen this being an important input for many different compounds. Protein binding, we can use the Hill-Langmuir equation to define the protein binding, or just specify the fraction unbound. Many times you'll just have a measurement of the fraction unbound, and that's fine. You can enter that in. Again, fraction unbound and cytosol for protein binding in the cytosol, or any non-specific binding as well inside the cytosol. So that's all the detailed physics I wanted to go through for these cell-based assays, and we'll get straight into the examples because we have limited time. The first couple examples are just going to be quick, model validation type exercises we looked at just to see that our new models were working. I'm going to go through them very quickly to get to really the meat of the situation, which is the link between MembranePlus and GastroPlus. So first off, we'll look at sodium taurocholate. It's a classically, it's all biliary excretion, and it's all actively transported because it has poor permeability. It's not lipophilic, and that's how our body recycles the bile acids. And so it's a good compound to look at in terms of biliary excretion. We were able to get data from Qualist, in particular the Guo paper from ISSX in 2014. This is a poster actually, but they also published papers on this data as well. All properties except for CAM values were from ADMET Predictor. So we predicted all the properties using ADMET Predictor module. The experimental data is shown on the bottom of the slide here. So on the left, you can see the concentration in the cells plus the bile, which is the closed circles and the dark line. The hatched line and the open circles are just the amount in the cells. This does not include the bile. And so during the uptake phase of the experiment for the first 20 minutes, drug is fed to the basolateral dose compartment at a concentration of 1 micromolar. It's uptake into the cells and it's effluxed into the bile. And then at 20 minutes, the donor phase is removed and fresh buffer is added with no drug. And then you're allowed to look at the efflux phase from the cells and the drug being effluxed from the cells into the basolateral compartment. And then you can see on the right there in the buffer, you can see drug accumulating in the basolateral side. Adding calcium versus not adding calcium modulates the tight junction opening and closing, and so you get more drug on the basolateral side if you lack calcium, and then if there's calcium present, then you get less drug into the basolateral side because there's less of that tight junction opening. So the actual mechanisms involved in the uptake and excretion, biliary excretion of bile acids are NTCP transporter is the influx transporter that internalizes bile acids into the hepatocyte cells. Once they're into the cytosol, the bile salt export pump, the BSEP transporter will efflux the drug into the bile. And then there's also MRP4, although recent studies have indicated that OST alpha beta is probably the major transporter that will efflux the drug back into the basolateral compartment. And this image is from the Guo paper poster in ISSX as well. So we set up our model with all 3 of those transporters. We assume that there's no stirring in the assay, a complete monolayer of cells. We used, again, ADMET predictor values. We added the cell input assay parameters in the table on the right. We used literature KM values shown in the table below. We didn't have data across a large range in concentration, so we couldn't calculate KM from the data, but we were able to find literature sources for experimental KMs in various species. And also these papers indicated that the KM values are similar across species, so we were able to use a mixture of rat and human KM values for this study. These cells are human hepatocytes, by the way. And then we were able to fit Vmax values to the experimental data and see if our model is able to predict the concentration profiles for the cells plus bile, which is the blue curve. The pink curve is the cells minus the bile or without bile. And then the red curve is the concentration in the basolateral phase, which we're able to fit very well. We got very good fits to the cells plus bile concentration and very good fit to the basolateral concentration, and we did pretty good on the efflux phase for the concentration in the cells without bile as well. So our model is able to predict the kind of profiles that are necessary, to predict these types of systems. So we're happy to see that. So now we want to look at our suspended hepatocyte model. How does it quantify the relative rate of influx transport versus metabolism in statin compounds? So we know statin compounds have high influx and much higher influx than metabolism, and we wanted to see if we could pull that out of kinetic data and see if our model performs well relative to the pain model, which is a compartmental model that was published in 2008. So the pain model is just a simple compartmental model with linear clearance values for passive and active uptake and metabolism in the cell. So on the plot on the left, there's a atorvastatin in plot A, and then cerevastatin in plot B, and we looked at modeling the concentration profiles for these two systems to see if we could match these concentration profiles and predict the relative rates of influx versus influx versus metabolism. So we got the physicochemical properties either from ADMET predictor or experimental data. Of course, statins have fairly low solubility in their neutral form, but they're acids, so they have reasonable solubility at physiologic pH. There's substrates for OATP1B1. The Km value for atorvastatin is around 1 micromolar. The Km for cerevastatin is about 6 micromolar. Atorvastatin is metabolized by CYP2C9, whereas cerevastatin is metabolized by CYP3A4. They have Kms of about 45 and 12 micromolars respectively. Those were used as inputs into the model. And then we calculated optimized the Vmax and the Vmax values for the influx and the metabolism and these the hepatocyte, suspended hepatocyte cells, and we were able to relatively well match these biphasic sort of kinetic profiles where you have very fast uptake from OATP1B1 at the initial time points in the experiment, and then you have slow elimination through the CYP enzyme clearance. And we saw that both for atorvastatin and cerevastatin. For the model results, we obtained Vmax values for the influx and metabolism, and then we also calculated the average influx and metabolism rate for atorvastatin and cerevastatin, and compared that to the linear metabolic clearance that Payne had gotten in his, from his model in his paper in 2008. And we got very similar values for the rate of metabolism versus influx. The influx rate we predicted to be, sort of an order of magnitude faster than the metabolism rate, and that was the same result as Payne obtained as well. So we were fairly convinced that our model is able to predict the right behavior and the right rates for metabolism and influx for statins, and so we were convinced that sort of our model is the right sort of model, and it has the right sort of physics in it. The thing that we like with this model is it's completely mechanistic. MembranePlus is based on all mechanistic system parameters. All the physiology is built into the model. Whereas in the Payne model, they fit the intracellular volumes, cell membrane volumes, membrane water partitioning coefficients, and then they fit the active uptake, passive diffusion, and metabolism as well. In this case, we had system parameters that we fixed for all the models. We didn't need to fit them for any of the cell parameters. And then what we fit here was just the Vmax values for the transporter and the metabolism. For atorvastatin, we did have to fit the passive diffusion because our prediction from structure wasn't very good. But all in all, we had to fit essentially 2 parameters versus 6. So that's the power of having a more mechanistic model. And also the hope is that more mechanistic models have a better chance at extrapolating to different conditions as well. But let's get into the meat of the examples I wanted to look into. That was just our models, new models working properly, and we think they are. And then we wanted to look at the real meat, which is how do we use these models to actually provide inputs for GastroPlus, because that's really the important thing, right? You could fit data or you can simulate data all day long, but if it's not, it doesn't provide parameters that are useful for in vivo simulations, then it provides little utility. But we're going to show you in these next 3 examples that we can use these parameters in GastroPlus, and they can be useful for in vivo predictions. So the first one is a simple IVIVE scenario where we're looking at the suspended hepatocyte metabolism of propafenone and pulling the kinetic parameters from this in vitro experiment and then simulating IV data in human and predicting the PK simply from structure, a complete 100% IVIVE scenario. So in this case, we used predicted properties for propafenone. It's a class 2 compound, a moderate log P, a fairly low solubility in its neutral form, but it's relatively soluble and ionizable as a base. So the pH solubility profile is shown on the left. We had suspended hepatocyte kinetic data for 4 different concentrations across a wide range in concentration of 2 orders of magnitude from 0.05 to 5 micromolar. This was enough of a concentration range where we could actually extract the Km and Vmax values for the CYP kinetics for Propafenone. By the way, this is a CYP 2D6 metabolized drug. And then the parameters there on the right for the incubation were used to do the kinetic model. So we were able to fit the Km and Vmax for this system to the experimental data. There is quite a bit of experimental variability in this case, but we were able to obtain a Km value and Vmax value, a very low Km value for this molecule of about 0.00778 micromolar and a Vmax of 0.0126 nanomoles per minute per million cells. So basically, we wanted to see if we could use this Km and Vmax value to directly predict IV data in human based on this in vitro experiment from the literature data. So what we did is we built a model in GastroPlus for a 70 mg dose for IV bolus administration. And then we created, we opened the enzyme, the metabolism and transports unit conversion table in GastroPlus, which allows you to convert your in vitro experimental values into in vivo values within GastroPlus. So those same values that I had just mentioned from the model, from the in vitro experiment, were entered in up here in this right-hand portion of the interface, which are the MembranePlus fitted values. We set the in vivo fraction to unbound because our simulated model is using all unbound concentrations. So we don't have to use the Austin or Halifax method to, sort of correct for any cellular binding in the assays, because we're predicting that binding to the lysosomes and membrane structures itself. We select hepatocytes as the assay type, and then we transfer the CYP2D6 Km and Vmax values to the enzyme table to predict the clearance within the PBPK model in GastroPlus. We use the default PBPK parameters, and all the phys-chem properties were predicted from ADMET predictor in this case. We used the Lukacova method for the the partition coefficient values, the KP values, and then we did an IV-IV extrapolation, IV-IVE extrapolation of the IV pharmacokinetics of Propafenone, and we got very good results. Obviously, not every IV-IVE is going to be as good as this, but this is a very nice result for this compound. The next example is using efflux data from Keiko cells as input into a GastroPlus simulation. So Digoxin is a classic PGP effluxed molecule. Troutman and Thacker put out a nice paper having apparent permeability data across 4 orders of magnitude in donor concentration in Keiko cells. And from that, we were able to determine both the Km and Vmax for their experiment. Km value is about 95.3 micromolars for this set of data here. And you can tell based on the roll-off and the apparent permeability versus donor concentration that looks about right. Right when you see the permeabilities change or decrease, that's where the Km value is. So we're able to accurately extract that Km value for Digoxin in this case. But the kinetic data wasn't there. This was just apparent permeability. So what we did is we collected our own kinetic data for Digoxin and Keiko experiment. We wanted to see if the same Km that we got from the Troutman and Thacker paper was predictive of our kinetic data that we had obtained from the Keiko experiments itself. So on the bottom, the series of graphs are the kinetic data for the apical administration of Digoxin into Keiko cell assays, and then using that Km value, predicting the concentration profiles out to 2 hours for these Keiko assays of Digoxin. And we only had to make slight modification to the model for the Vmax because there's always going to be a slight difference between the expression levels from one lab's cells to another. So, but the Km value accurately predicted the dose concentration response of Digoxin Keiko cells. This is just the apical administration. We also did the basolateral administration, which isn't shown here, and we got similar results as the apical administration. Okay, so does that KM value, can that be used for an in vivo simulation? So again, we want to move over to GastroPlus and see if that in vitro, these parameters extracted from MembranePlus are valuable in defining our GastroPlus simulation inputs. And so we built a model for Digoxin using a KM value of 95.3, which was extracted from MembranePlus. And we built models for human IV bolus at 1.5 megs, and then a much lower dose as a PO tablet in humans of 0.25 megs at 2 different particle sizes in at 6.5 micron and 51 micron. So the IV bolus is the plot shown labeled A. The human PO tablet at 0.25 megs are in plots B and C. Plot B is the low particle size, plot C is the high particle size, and we're able to predict with that KM value across an order of magnitude roughly in doses concentrations, IV and PO administration, fairly good results using that KM value. Of course, you do have to do a scaling for the in vitro to in vivo Vmax because of differences in expression levels between the in vitro experiment and in vivo. But the KM values you extract were predictive in this case. So that's the second example of how you can use MembranePlus to populate inputs in your GastroPlus simulation. And then the third example, the fifth example total we're going to look at is lysosomal trapping. And this is what I was talking about earlier. We kind of glossed over it. We talked about how basic compounds can easily permeate into the lysosome, and then because of the pKa of the molecule being between 6 and higher, the solubility in the lysosome is going to be much higher than in the cytosolic space, and so drug can partition into the lysosome and be trapped in that lysosomal compartment. And so we looked at a compound from this paper from Zhang in 2013. It's a named compound X. It's a BCS class 2 compound. It's lipophilic. It's a base. It's got low solubility. So the solubility within the lysosome at pH 4 is predicted to be much higher than in the cytosol. There's a definite chance of lysosomal trapping. It's got fairly decent permeability, and so we wanted to see if we could predict the PK of this compound. And there was fasted and fed PK studies at 200 and 400 mgs for this drug. So all the compound properties we were able to pull from the paper on the left. So we had the pharmacokinetics and we had a 2-compartment pharmacokinetic model we were able to use from the paper. We had all the inputs, experimental solubility, we had pKa, we had all the different properties necessary, particle size to define our model. So one thing to note here on the PK data for compound X is that one curious thing is that it had fairly extended Tmax out to about 5 hours in many cases with these with the PK data of these compounds, both in the fasted and fed state. And we wanted to really determine if we could predict this. And this compound is basic in it's got low solubility at physiologic pH, so there's also the potential for precipitation. They show here in their paper that they needed to use a precipitation time of 450 seconds or 2,000 seconds in the fed state to predict the PK. So we built a model and we said, okay, can we use these types of parameters and get similar results or good results for the model here. So we built a model with default model parameters in GastroPlus using the inputs, and it doesn't fit very well. We have much too high of absorption, and the Tmax is only about 0.8 hours for this compound because it's got fairly good permeability and it's soluble in the gastric, so you get a lot of drug on board absorbing in the duodenum. You get a very short Tmax, and we're over predicting the PK. Now you can adjust. You could say, okay, well, maybe there's going to be precipitation, of course, because this is a basic compound. So we, cranked up the precipitation rate, and that gets you closer in Cmax, but it doesn't change the Tmax. You still get a Tmax value that's, Tmax value that's about 0.8 hours, and it doesn't predict the kinetics even close to correctly. The onset is much too high. You can see here on the absorption and dissolution curve on the right that the drug is essentially almost instantaneously absorbed into the enterocyte and the upper GI tract, and then gets into the portal vein. And so we just don't see the correct Tmaxes or kinetics being predicted in this case, using the same sorts of inputs stated in the paper. Okay, so we said, okay, this is a basic compound. It's likely can be stored in the lysosome. So as it's permeating through the intestinal epithelial, the enterocytes, it's likely partitioning into the lysosomes in those cells. And maybe that's acting as a sink for the drug and delaying the drug reaching the portal vein. So what we did is a parameter sensitivity analysis, looking at fraction unbound and enterocytes all the way from 0.01 to 1, which is 1% to 100% unbound in the enterocytes. And we tried to look at, sort of what would the likely FU enterocyte value needed, what's the likely value needed to predict the Tmaxes in these studies. And we see about 3.6% FU enterocytes. And that got us thinking, we have this really good mechanistic cell model. Could we have just predicted this to start with? I mean, what's the rationale for this? Can we use a mechanistic understanding to really provide inputs for this model and provide better results? And so we built a model for compound X within MembranePlus using those same inputs from the paper for the phys-chem properties. And then this is just a 12-well experiment in Keiko cells. And we wanted to predict what the cellular disposition of compound X is. Of course, we do see lysosomal trapping because of the compound properties. As you can see, the lysosomal concentration is much, much higher than the cytoplasmic concentration. So really the concentration in the cell is determined by what's in the lysosomes. And there's a fraction unbound in those cells of about 3.47% based on our MembranePlus simulation. And so voila, this shows us, this validates the PSA that we did, and we have a very mechanistic, rational understanding of that input and how it affects our GastroPlus simulation. So we directly enter that value into GastroPlus using the power of our mechanistic cell simulation model and MembranePlus. So we built a model with the FU enterocytes from MembranePlus of 3.47%. We ran the model and we got very good results as far as the initial kinetics of the drug entering the bloodstream. So here you can see what happened as we increased the or decreased the FU enterocyte value from 100% unbound to 3.47% unbound. You can see this delay that occurs between the amount absorbed in the enterocyte to the time it gets to the portal vein. And this delay caused by that FU enterocyte that's all predicted from MembranePlus determines the kinetics of the, and predicts the Tmax in this case. So we were able to do a fairly good job, and this is the 20 mg IR capsule that's in the fasted state. So how did it predict the other formulations, the 200 mg fed and the 400 mg formulation? So we ran the model against those formulations as well, and they fell within the error bars of the simulation. Also predicted the correct Tmaxes. We could get a little bit more, fine-tune this model a little bit more, and we could lower the colon fluid volume to a more reasonable value of maybe 2%, and we could get a better simulation. But I didn't want to change too many parameters. I just wanted to show you the mechanistic inputs that we got from MembranePlus, and just show you that that really was critical in this case of predicting the correct Tmax values. really do minimal amounts of fitting in this case. All we had to do is change the precipitation time to similar values that they had shown in the paper as well. So again, MembranePlus provides critical inputs for the FU enterocyte that allows us to predict in vivo simulation results in GastroPlus. So the conclusion here is that MembranePlus has a bunch of different capabilities to assess passive and drug-active transport and all the different assays from CACO, MDCK, PAMPA to the new models, which are sandwich and suspended hepatocytes, drug disposition in bile, and then also the lysosomal trapping within, lysosomes, and then look at the concentration in all the cellular structures. And we can extract relevant parameters for IV, IVE. We can extract relevant KM parameters and Vmax parameters for metabolism and or efflux or influx transporters, and we can also predict the FU enterocyte values for GastroPlus simulations that allow you to really look at the extended Tmaxs of lipophilic cations, basic compounds. So with that, I'd like to thank the Simulation Technologies team, which I am a part of, and also Kay, who worked on very hard on version 1 of this software and helped, with bug testing and whatnot in version 2 as well. Of course, Vera, our team leader, and then Mike Bolger, our chief scientist. And then we had support from other teams, computational technologies, chem informatics, and consulting studies. So with that, that's the end of our presentation today. It's been nice talking to you, but let's get into some questions, and I'll let John moderate here for that.
Okay, thank you so much, Jim. Very good job. Once again, if you'd like to ask a question using your telephone, please use the hand-raising icon on your control panel and be sure to enter your unique audio PIN. So there have been several questions coming in written, so we'll start from the first one received. Does the Transwell assay setup take into consideration the contribution of paracellular transport based on a measured TEER, T-E-E-R value?
Yeah, I mean, right now we have a TEER value in our model as far as bookkeeping, but what you would have to do is convert that, sort of TEER value into some sort of, maybe you could adjust the electrical potential gradient in that case, or something of that sort. We don't have a direct link from TEER to any of the parameters currently. You would have to make some sort of modification, either maybe to the pore radius or the electrical potential gradient of the cell, in that dialogue that I'd shown in the presentation. So we don't have a very good link as of yet, but of course that's one thing we hope to add in the future.
Okay, thank you, Jim. Next question, is the volume of lysosomes constant across the various cell types? So for example, CACO versus hepatocyte.
Yeah, for now it is, but we're looking at getting data for all the different cell types. It's difficult to find this data. Not many people do these self-fractionation studies, so we have found data for hepatocytes, but we're looking for better data, for the different cell types. So as we come across it, we'll add it to the software itself, and it's a parameter that you have complete control over. So if you want to measure that yourselves and update your cell assays as you see fit, you're allowed to do that, and you can save your own user-defined membranes as well.
Thank you, Jim. Another question, with statins in general, can you account for the permeability of the lactone and acid form simultaneously?
So right now we're not doing that. And also in the future, and this is going to be version 3, we didn't talk about what's coming in the future, but we plan on looking at all the metabolites and any sort of other species you may want to model simultaneously. And so in the future, we plan on adding these complexities. We focused on adding the new models at this point And then, we're going to look at drug-drug interactions and, tracking metabolites in the in other species in the next version. So that'll be in version 3. So stay tuned.
Thanks for the teaser, Jim. Next question. Have you examined the permeability in the presence of baflomycin that dissipates the lysosomal pH gradient?
Yes, and I think you can find this maybe on our website, or I don't know if it's still on YouTube or not, but we have the whole, basically we did the same webinar for the release of version 1, and we go through that exact case for propranolol, showing, baflomycin or proton pump inhibitors, adding those and seeing the effect, so we do have examples of that. We didn't show it here because we've shown it many times previously in other presentations. I urge you to go look at that presentation. We probably have a link somewhere on our website, and you can look into those examples. But we have looked into that, and we have data on that, and it should be available somewhere at our website, I would think.
Yeah, thanks, Jim. On the Resource Center, you would be able to find both a webinar recording from previous examples that have been presented with MembranePlus, along with some work that we've presented at conferences, I believe several posters that go through some of those examples as well. So it's all available on the Resource Center at the Simulations Plus website. Next question is, can the saturation of lysosomal trapping be modeled in MembranePlus?
The saturation, so I mean, the amount of drug in the lysosomes is going to be determined by its, essentially its maximal solubility at that pH. So the saturability is, essentially what we're assuming is the solubility at that pH. We don't assume more drug than that can be, partitioned, into the lysosome. That wouldn't make sense in terms of concentration gradients and whatnot. So our model, is mechanistically determining what the concentration gradients are and the speciation between the charged and uncharged form. So that's all taken care of in the sort of theoretical equations. So I don't know if that answers the question, but that should all be taken care of based on the physics involved.
Thank you, Jim. The next two questions may be more for Vieira. First is, where in the GastroPlus program can you input the fraction unbound in Enterocyte, or where can it be modified?
It is kind of a tricky setup right now. You do have to go into the drugs table to modify it, but if I'm assuming this question was asked by somebody who's somewhat familiar with GastroPlus. So if you go into the menu database, view edit tables, view edit drugs table, in that table you will find a column percent unbound enterocytes. That's currently the only place where you can modify this parameter.
Thank you, Vera. Another question. Adjusting the fraction unbound in the enterocytes nicely captured the delay Tmax for the basic compound. This adjustment will modify the simulated intra-enterocyte free concentration profile quite much. How do you expect this to impact the performance of DDI predictions involving inhibition or induction of gut wall enzymes?
So, let's say let's talk about, let's say, CYP3A4 in the intestinal, the enterocyte. It's obviously going to decrease the free concentration. And so all our Km and Vmax values are based on intracellular concentrations, right? So that will modify the metabolism rate. So yes, it will have an effect on that free concentration and the metabolism rate. So in this case, we don't have any we didn't have any data as far as the any of the metabolites or anything in the intestine, but yeah, it would be something you would need to look at for a compound that has a large first pass metabolism, let's say in the intestinal epithelial cells. You would want to make sure that it's all consistent, you know, the amount that's being metabolized versus your fraction unbound in your enterocytes. That's a good point. And, you know, it gets very complicated, but certainly you can't deny the fact that, you know, basic drugs are going to partition in lower pH cellular structures like lysosomes, and we think that that is an important point in the model. But yes, you are correct. It will lower metabolism rates for the in the intracellular space.
If I can just quickly follow up on that one, we have just recently been working on a model for diltiazem and its metabolite, where both are time-dependent inhibitors of 3A4, and we've used the strategy that Jim outlined here, use the MembranePlus to predict the FU enterocytes and use that as an input in the model. And that model actually did allow us, or is now validated in terms of describing the PK of diltiazem as well as describing its effect on 3A4 using 2 or 3 different substrates, you know, 3A4 substrates. So from the point of perpetrator, you know, we've recently worked on at least one of these validation cases where it did a very nice job. From the point of substrates, I think we need to find good examples where the substrate would have the significant lysosomal trapping, and we would also have data for DDI to actually validate how it affects the metabolism.
Thanks, Viera. Thanks, Jim. I don't see any other questions at this time. And seeing that we are about 7 or 8 minutes past the hour, we'll wrap things up. So I want to thank again Jim for the really excellent and insightful discussion today on MembranePlus version 2, and especially how some of these outputs from the program are able to now better inform some of the inputs for your GastroPlus PBPK models. If you missed any part of the discussion today, as mentioned earlier, the playback will be available at the online resource center on our website, www.simulations-plus.com. Also, please keep your calendars clear for the same time next week, Thursday, September 14th, as researchers from GlaxoSmithKline will be presenting on the novel mechanistic dermal absorption model in GastroPlus as part of the GastroPlus user group webinar series. Details to register are going to be sent out today, so stay tuned for more information. Thanks again, everybody, for joining us, and have a very wonderful day. Bye-bye.